Hey guys, it's Chili here. Welcome back to 3D Fundamentals Tutorial 14. Today we're starting on what is the most interesting and probably the most important topic in 3D graphics rendering. I'm talking about dynamic lighting and shading. So, let's get started here. Take a look at this image here. What does it look like? It's a circle, right? It looks like a flat circle. Now look at this one. Now this one decidedly looks like a sphere. What's the difference between them? They're both about the same color. They've got the same outline and shape. But obviously this coloring here, this shading if you will, this is what allows our brain to perceive this as a three-dimensional object and this as a two-dimensional object. Geometrically they're the same. They're just a circle really. But the color on there is what allows our brain to perceive the three-dimensional topology of this object. Like I said, a big theme of this series is going over the visual cues that allow our brain to perceive 3 dimensions through a 2-dimensional screen. And some of those are perspective, occlusion, and another one is, the big one is the shading here. Now, before we get into dynamic lighting proper, we need to talk about different light sources, specifically point lights and directional lights. So if you've got some particle in space, and let's say it's emitting photons, it's going to emit them in a manner like this. And if you've got some surface, the light rays, they're going to strike the surface at angles like this. Now, if we move that point source farther away, the same as this light source, it is going to be emitting light in all directions. Now, if we look at the light rays that strike the same points on this surface as the light rays from the closer point source, we're going to see something. The angle between these light rays is smaller than the angle between these light rays. And if we pull it out even further, what you're going to notice is the angle between the rays is getting even smaller. The rays are getting more and more parallel. Now, if you pull this point light source away into infinity distance, what you're going to get is you're going to get a situation where the light rays are all hitting the surface parallelly. Okay? There's no longer any angle between them. They're all hitting it at the same angle. Now, you can't actually pull a light source away into infinity, but you can have a light source that is incredibly far away compared to the size of your scene. For example, the sun, which is a very common light source, is generally just considered a light source at infinity. So the light from the sun can be considered as light like this. We call this directional light. So directional light, it's all coming in, it can come in from any direction, of course, but all of the light rays are parallel and they're all going to hit a surface like this at the same angle. This is very important. All right, so let's take a look at this 2-dimensional setup that we got going here. I've got some directional light source, and the rays from this light source are hitting some surface here. And those rays are now going to be scattered all over the place, going in all directions basically. And some of those are going to enter the eye of the viewer. And it is from these that the eye will be able to see this surface here, this board or whatever you want to call it. Now, the brightness of this board depends on a few factors. One of the factors is obviously the intensity of the light. So the more rays you have, the brighter the board is going to appear. Obviously, if you have no rays, you're not going to see the board. If you only have a few rays, only a few are going to be reflecting off and entering into the eye. Now, let's take the same board. We're going to take the same intensity of light, the same density of flux here. Same board, but we're going to angle the board differently towards the light source. Now what is going to happen? Well, you've got the same 1 meter of board, but you're going to have fewer photons hitting it per second. So the density of photons across this length has been cut in half now. So now you're going to get half as many photons that bounce off this thing and actually enter the eye of the viewer. And so this is going to appear dimmer. And this is where the concept of shading comes from. as you angle this surface away from the light source, its cross-section in the stream of light becomes smaller. So it is getting less light that has to be distributed over the same length of the surface. And so the surface is going to appear dimmer because the density of photons on this surface is going to be lesser. And if you increase this, if you angle the surface exactly parallel, side on to the light, none of the photons are now going to be hitting the surface. So it's going to appear black now. And you can actually test this out yourself. If you're sitting in a room and you've got a single light source like a light bulb, take a flat sheet of paper, angle it so that it's pointing directly towards the light source, and then tilt it away from the light source until it is pointing side on to the light source. And you will see it getting dimmer and dimmer. Now, it's not going to go completely black because, of course, there are light rays that bounce off the walls and then hit it from the other side. So you're never going to get something completely black. You could do that basically if you went into outer space. But yeah, this is the basic concept of dynamic lighting. And this is what allows our brains to perceive the features of this face here, for example, because the light is going to be hitting every one of these polygons at a different angle. We're going to get a different kind of shading on it, and our brain can take these different shades of color and reconstruct a three-dimensional model inside of our brain to recognize what this thing is. It's amazing. It's kind of reverse engineering of these different gradients of light into a three-dimensional mesh in our brain. We can understand the features of this model here. All right, that's nice and everything, but what we actually need to do now is we need to use math to figure out the intensity of the light coming off of any given surface, because we need to calculate that to calculate the color that we're going to shade our triangles with. So let's say that our light source here, our directional light source, the density of the flux of photons is going to be 10 per meter, 10 whatever, it doesn't matter. Now we're going to angle a 1 meter plate, and the angle here, this angle, is going to be pi over 6 radians, which is 30 degrees. So what do we got here? Well, the intensity is just going to be I times whatever this length is here. So the smaller this length is, obviously, the less photons are going to be hitting the surface, and the dimmer it's going to look. Now, this length can be calculated with simple mathematics, right? It's just sine theta, right? Sine whatever this angle is here. And the sine of pi over 6 is going to be 0.5. So if you are angled 30 degrees towards a light source, you are going to get half of the intensity of the light. Half as much photons are going to hit you and be scattered as would if you were angled directly towards it. Now, this is fine, except for, a couple problems. We don't have the angle of our surfaces in degrees or radians, and furthermore, calculating sine is, very slow. We would like to do vector operations. Can we do that? Well, we know that the dot product of two unit length vectors is just equal to the cos of the angle between them, right? Now, cos, this seems pretty similar to this one. We're just off by a little bit. Can we massage things? And the answer is yes, we can. So if we take the face normal of this surface, and we measure the angle between that and these light rays, we're going to see that angle is actually pi over 2 minus theta, which is, 90 degrees minus theta. And it just so turns out that the cos of pi over 2 minus theta is equal to the sine of theta. So if we use our face normal with this light direction normal, we can calculate this intensity factor. Now, there is one problem with this in that our light is pointing in this direction, but the normal coming off of our face is in this direction. So they're pointing in the wrong directions here. And all you got to do to fix that is just flip one of them. So you can, for example, flip your light vector into this direction, or you could have flipped your face into this direction, and then the angle between them will be the proper angle needed to calculate this stuff. So to get the brightness on any face, all you're basically doing is you're calculating I, the intensity of the light source, times L hat, which is the direction of the light source, dot N hat, which is the normal of your surface. And then you just add a negative in there to account for the fact that you have to flip one of those guys. And there you go. You've got your motherfucking lighting calculation. And it's pretty simple. And it uses the dot product, which is very fast. And this is basically at the heart of all dynamic lighting, all lighting in 3D engines, which is probably the most important visual cue you're going to get for understanding a three-dimensional scene. And it's super fast because, as we all know at this point, the dot product between two vectors, you could calculate it with cosine, but we don't do that. We calculate it the other way, just by multiplying the components together and adding up the results. All right, now let's get into the code and see how we're actually going to implement this. So there's a couple of ways we can do this. The first way is we could store, let me get a little picture in here. We could store the normals, because we need the normals, right, to calculate the shading. We could store the normals in the vertices, but this is going to cause a problem in that we can't share vertices between these different faces. It's not going to work, right? Because this vertex, for example, depending on whether it's drawing this triangle here, or this triangle here, it's going to need a different normal. So we're going to have to use the independent face setup. So instead of having 8 vertices, we're going to have, I believe, 24 vertices, I believe is the number we need. Anyways, we've already got the function in cube.h to do an index triangle list get plane independent faces. So we can get the independent faces, all the coordinates. Now to that, we need to add the normals. So I create another function, get independent faces normals. And first of all, it calls get plane independent faces with some templated vertex type. And then after it has generated the vertices, all of the coordinates, it adds to it the normals. And the normals I just calculate, by hand, just by freaking looking at this diagram here. You can, not that one. You should be looking at this diagram here. You're going to see, okay, so when I'm drawing, vertex 3, when I'm drawing this face, the normal is going to be, z is equal to -1, and the x and y are 0, and so on and so forth. You don't need any particularly difficult math to figure out what the normals are for any given vertex, for any given face. So we just a bunch of typing out there, and then what is this? Now here's the scene, doesn't really matter. The important thing here is the mother freaking, what did I change in Vec 3, by the way? Okay, so I added a bunch of functions in here, and they are going to be useful for calculating the colors of things, but we'll get into that in a second. Let's look at the vertex flat effect, because this is where all the action is going to be happening. So we're doing it per vertex. That means that all the work is going to be done in the vertex shader, I believe. Well, in my discussion, I just treated light as a single value, so it was only just a black and white grayscale light. But in real life, light, you can have different colors of light. So here we treat light as a 3-channel vector, red, green, blue, right? And you've got 2 different kinds of light. Diffuse light is the light that I talked about. That's the light that we're going to be using for our dynamic shading. The other kind of light is ambient light, and that is the light that you get from, stray photons that are bouncing off the walls and hitting your stuff at different angles. So this is the indirect light, and it basically contributes to, for example, when the object is facing away from the light source, it doesn't just turn invisible, right? You can still see it, it's just a little darker. So the ambient light is the part the indirect part, and diffuse is the part that is contributed from the flat shading. And color here, that is the color of the object. So it's basically, you can think of it as a filter. Color is how much of each channel this object is going to reflect. So our object here, it's reflecting 80% of the red, 85% of the green, and 100% of the blue. So by changing these values, you will change the amount of light that is the ratio of the different channels that is reflected, and that is going to determine what color that object appears at. And then here we've just got the direction of the light. So the light here is starting off facing in the Z positive direction. And here is all you need for your dynamic lighting calculations. So we multiply the diffuse color vector by the normal of our object times the direction of the light source, and that's negated. And the reason why we have this rotation is is because our object rotates right. So the normal also has to be rotated depending on the current orientation of the object. So just like you transform all the positions, you also have to transform the normal. You don't have to transform it in space. You don't have to do a translation of it, but you do have to rotate it so that it is in the correct orientation for when you do your light calculation. So here we go. We've got our light intensity times our normal of our surface times the direction vector. And there you go. There is your diffuse component. Now, we have to add together the diffuse plus the ambient component. That'll give us the total light hitting that surface. And then we have to multiply that light vector by the pigment, the color vector of our surface. So this is called a Hadamard multiplication, because what we're doing here, let me show you. We're not doing a dot product where we multiply them all together and add the sum up the products. We're not doing a cross product. All we're doing is a very simple multiply across. R times R, G times G, B times B, and that's called the Hadamard product. So that is why I added that to the vector class. So we take the color, the pigment of the surface, and we multiply that by the intensity of the light, and that gives us the light that we're going to see. But we don't want that to go above 1, basically. 1 is full light, and we don't want it to go above that. So we saturate, and that will clamp it to maximum of 1, and I believe minimum of 0. I'm not sure if I do the minimum test in there. But anyways, then we multiply by 255 because our integer colors range from 0 to 255. And that's it. That's the lighting. Just these two lines for the dynamic lighting. This for the rotation, the translation, the transformation of the vertices, their positions. And then we just return a new vector. The output of the vertex shader just has position plus the color. One thing I forgot to mention is the stid max in here. This is important because if the surface is facing away from the light, you're going to have a negative result. But you don't want negative light, doesn't make any sense. So we want to cap it at 0. The minimum that light can be coming off the surface is 0. You can't have negative light. It can't be sucking light into it. And there you go. You've calculated your light. You've got every vertex now has a color on it. And in here, in the pixel shader, you just return the color. There isn't even any interpolation required between the different vertices because they're all going to have the same color for any given face. And if we run that, we've got our cube now. And here you can see it is being shaded. You can use the normal keys to rotate it, to bring it in and out. And you can also use UIOJKL to rotate the light vector. And here you see, when the light vector is pointing away, now all we're getting is the ambient light, which I set to pretty low because it looks like we're in outer space, basically. So yeah, it looks good, but it is kind of boring. Like all we're seeing is cubes here. We can't see a lot of definition. Now, pre-calculating and storing the normals per vertex is one way we could do this, but we could do it another way, right? Because we've got our geometry shader now. So what we can do is we can store our cube in the minimal required geometry of only 8 vertices. And then with our geometry shader, we can expand that to single triangles with the normals, and we can calculate the normals at runtime in our geometry shader. So let's try and do that. So for the geometry shader, it's pretty simple. We use the default vertex shader. All it's doing is transforming the positions. In the geometry shader, what do we have? So here we store the direction of the light, diffuse, ambient, and the color of the material of the surface. And yeah, again, we got setters for all of those things to set them up. And in here, we're doing the same thing, right? We're calculating the diffuse, we're calculating the color, and we are jamming that out as a triangle, 3 vertices like that. The only difference is we're, instead of having the normal stored in the triangle vertices that we get in, we're calculating that ourselves, just using, the thing that we used for backface culling, the cross product here. And if you run that, you see you get the same result. It's the same thing as happening, just a little more elegant in my opinion. Although I don't think that is the technique actually used for flat shading. I don't think they use the geometry shader usually for that. They probably just duplicate the vertices. But it's one way you could skin that cat, and it's a fun little use of the geometry shader there. It's very elegant. It only uses the position information to derive the normal, and then use that all dynamically at runtime. Now, these cubes are getting kind of boring. You know what I'm saying? We've got this cool flat shading technology. We need something a little more interesting to test it out on. So what I decided to do is I decided to add support for loading OBJ files, which is a kind of 3D model file format. And they look like this. Basically, the simplest one that you can get just has a list of vertices and their positions, and then a list of faces and what vertices those faces have. So it's an index type of geometry here. You got your vertex count, your face count, etc. Very simple file format, and it's not too hard to write your own loader for it, but I decided, why would I do that when there's perfectly good ones on the internet? So I added tiny object loader, and it's tiny, but it's still 2,000 lines of code here in the H file. And then in index triangle list, I added support for loading from an object file. And basically the way you do that is, all right, well, there's a bunch of things. First of all, object files can be counterclockwise or clockwise winding, and it's not clear which one it is. So I've added a little extension to the file format where if the first line, if it contains CCW, then it will be determined to be a counterclockwise winding model. And that's easier than me just converting all the models I download off the internet so that they all have the same winding. So you create, using namespace tiny object, and just attribute, so declare a thing that I'm going to be using for getting attributes out of objects in there, and shapes, got a string there for the error. So first you do the load object, and this API works by passing in pointers to all of the things, and then you access it. I don't like it that much, actually. It's not my favorite, but it's fine. It's fine. Who cares? It's just a API. I'm wrapping it up myself anyways. So I load the object, giving it the file name, giving it a place to store errors, giving it a place to store shapes and attributes. And then I check for some errors. I throw if I find any. And then I extract the vertex data, which is basically in the attributes, there is a thing called vertices.size. And there you can see how many vertices you have. And I just do a for loop through that, jumping up by 3 every time, 3 vertices per triangle. And I jam those guys into my own vertex vector. And then I have to extract the index data for those vertices. And that works, I wouldn't say it's super straightforward, but it's also not that complicated. So an object file can contain multiple meshes, but the ones we're loading, they're only going to have one mesh. So I just do a little alias here. Mesh is shapes0.mesh. And then there's a bunch of vectors in there. One of the vectors tells the number of vertices for each face, because you can have models that are not triangles. They can be made out of quads or larger polygons. So we're going to loop through all of those. And the first thing we're going to do is make sure that it's only 3 vertices, because we only want to deal with triangles. And if we find one that isn't, then we're going to throw an error. So here we're just checking to make sure it's all triangles. And then in here, we are actually extracting the indices and putting them into our own index vector. God damn it, I hate these words, vertex, vector, And sometimes a vector is a mathematical vector, and sometimes it's a container. Grr. Anyways, we do this for each face. So for each face, we put the indices into our own index vector. And then if the file is counterclockwise, we just got to swap the order of two of those indices to make it clockwise. So as I'm loading it, I am translating from counterclockwise to clockwise if necessary. And that's it. That's all you need to load a model. And then in game.cpp, I just add a new scene in here for the geometry flash scene. But instead of passing it just plain cube, I am going to pass it, I'm going to load models bunny. And here you go, beautiful bunny. It's a little far away. Let's bring that in for a second. All right, here you go. Here is our beautiful bunny bro. And as you can see, it's not the vertices. They weren't defined around the center of the model. They were defined around its base. So it's a little weird to rotate. And it's also difficult for me to figure out a correct zoom for it based on that. So that's a little bit of a problem. But you can see here, if I rotate the lights, very sexy. Don't you think that is sexy? Because I do believe that that's giving me a little bit of a chub right now. Not gonna lie. But yeah, so there you go. There's the flat shading with a little better model. Now, the fact that not all of our models are going to have the same center, they're not going to be properly centered, it's going to cause some problems for me. So what I did, I downloaded a little different library, some open source stuff called miniball.h. And what miniball does is it basically allows you give it a bunch of vertices, and it will calculate the basically the minimum sphere that can contain all those vertices. And then you can get the center of that sphere, and that will be the center of your model. And then you can use that to resize or to zoom in to the model so that it is zoomed up to just fill the viewport without going outside of it. And you can also use the center of that sphere to readjust all the vertices, so when you rotate it, it's going to rotate about its true center. And using that isn't that complicated. All you got to do is, so what do we got here? So you need to create a little bit of a structure here that gives information to this algorithm to allow it to access the data from your vertices. So you type def a couple of things here for this function. I guess this is the iterator over the vertices, and this is the iterator over the elements of the vertices. And then here's a little operator that allows it to access the element. So this will give it access to the first element, the x. And then it can use iterator float to access y and z. And then we pass the mini ball. We create the mini ball with our vertex accessor. We tell it there are three components, which are going to be x, y, and z. And we give it the iterator to the for the first and the end of all of our vertices. And then once we create that, it just processes it, and then we can get the center of the minimum bounding sphere. And we create a vec3 based on that information, translate it into our own language, as you will, and then we adjust all the vertices so that they are now centered around this new center, just by subtracting that from every one of their positions. I also added a function, a general function here, get radius. Yeah, so this is for index triangle list, and it'll just go through all of the elements and get the max distance from the origin, and that's the radius now of that object. And then here I just adjust the center. In geometry flat scene, I adjust the center of the model, and then I set the offset based on the radius so that it's just enough to basically fill the viewport without going outside. And if we run that, we see our rabbit now starts at a good zoom, and it now rotates a little more manageably. And yeah, it's just a little nicer there. Who's a cute bunny? Who's a cute bunny? You are. You are. All right, you probably didn't want that, did you? Who's a cute bunny? And the last thing I did, just for a little bit of shits and giggles here, is I have added flat shading, dynamic lighting to the wave vertex texture effect. So now we're going to see lots of things going on. We got the vertex shader that is deforming the geometry, creating the wave. And then we've got the geometry shader that is using that geometry to calculate the normal and then calculating the lighting based on that. And then we have the pixel shader, which is getting the texturing information and using that plus the lighting to calculate the final color. And if we mess with the light direction, we can get a pretty interesting wave effect going there with the dynamic lighting. You see that? Looks pretty sexy. You can also kind of see, because the lighting is very pronounced here, you can see the individual tessellated triangles now that make it up with this flat shading. I just got a bad feeling that Git has been ignoring my model files because their file extension is .obj, which is the same as, C++ binary objects. So I'm gonna have to do something with Git to make it not ignore my model files. We'll see what that is. But anyways, that is going to do it for this episode. This has, I hope you will agree with me, this has been very epic, very important, and this changes everything, shading. And I hope you will also agree that it is actually not that complicated. It all just boils down to this formula right here, simple dot product between vectors, and Bob is your uncle. In the next few videos, we are going to explore more and more advanced types of shading. We just done flat shading, but there's also the smooth types of shading of per vertex and per pixel shading. And there's also the ideas of specular highlights, these little shines here. Plus, we've only just worked with directional lights. We still need to figure out how to do this stuff with a point light source. So a lot of good stuff coming up. This is what I consider to be the meat of this 3D Fundamentals course. We're getting into the meat. And once we're done with the meat, there's not going to be much left before we get into hardware 3D. But that's going to about do it for today. Thanks for watching. I hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more 3D fundamentals.